In the next few lessons, we're going to look at how to measure experimentally the reaction rate of a chemical reaction. In this lesson, we're just going to look at the basic principles involved. So when we're measuring the reaction rate, what we're doing is obtaining some type of graph that looks like this. So we're going to be measuring the amount of product that's evolved and how that changes with time. So what that means is over a given period of time at regular intervals, we're going to measure, for example, we might measure the change in mass. Okay, this might be the change in mass. That triangle means change in mass, or it might be the change in volume of a gas that's being evolved during the reaction. Okay, so this is the first stage, is we need to obtain a graph like this. So we'll look at how we do that experimentally in the following lessons, taking particular examples. But once we've obtained this graph, then what we've got to do is find the rate of reaction. So we want to know the rate of reaction at a given time t. So that's equal to the amount of product revolved in a given unit of time. So for example, if you want to know the reaction rate at some time t, let's just say there, for example. Okay, so what we want to do is, once we've measured how the product evolved changes with time and we've plotted our graph, whether that's mass or volume, then at that particular time t we need to measure the slope or gradient of the graph. So this slope here of the graph is equal to the rate of reaction, or the reaction rate. Now, you won't really be expected to calculate slopes like this, I don't think, in your IGCSE, GCSE exams, but what you really need to understand is how to interpret these graphs qualitatively. So to recognize that the slope of the graph tells you the reaction rate. Okay, so just looking at this graph, you can see that as time progresses, the slope of the graph initially starts off quite steeply. Okay, so there the reaction is going quite quickly, and then gradually the slope gradually gets less and less, so the rate of the reaction gradually decreases. Okay, so we move on again another sort of equal time interval to that point there, and we see that the slope is less. Then we move on again by the same equal time interval, and we see that at this point the slope is less. So gradually the slope of the graph is getting less. So you can think of it, as a hill or a mountain. You can see that initially, it's quite high. It's quite difficult to walk up that mountain because the slope is very steep. But gradually, as we keep walking up the mountain or the hill, the slope gets less and less. So the reaction rate, as the reaction progresses, is gradually decreasing, and that's going to be the same for any chemical reaction. Okay, so it is possible, for example, that you might be asked to calculate the initial reaction rate. Okay, so that's the reaction rate at time t equals 0. So you might be asked to do that. So looking at this graph, then how would we do that? Well, we calculate the slope at time t equals 0. So we've got to draw our tangent to this curve. Okay, that's the slope. And then what I need to do is to determine the vertical change. This might be a change in mass, or it might be a change in volume, for example, and divide that by the change in time, which is the change along the horizontal axis. That's delta t. So I'd need to measure from my graph this value, and I'd need to measure this change here, and then I just slot those into this equation. So the reaction rate would be delta m or delta v, depending on what you're measuring, divided by delta t. Okay, so you might be asked to measure the initial reaction rate of a chemical reaction, but really it's all about qualitatively understanding the results that you've obtained. Okay, so for example, we might be measuring the product evolved against time for some chemical reaction. Let's say it's the reaction between A and B, two imaginary substances, and that gives us C plus D. It doesn't matter what they are. What we're doing is we're understanding, what these graphs mean, and so First of all, you can see there, for each graph represents exactly the same reaction. We've got exactly the same amount of reactants, A and B, each time the same mass of A and the same mass of B in each case. And so we've got the same amount of product evolved. So we've got the same amount of reactants, and that gives us the same amount of product. Now, what you can see is that the three graphs are very different. We've got the blue, the orange, and the red. And in the case of each graph, the reaction is going at a different rate. So, for example, we could take some time t, let's just say there. Now, I should mention that this is clearly the time when the reaction starts. And at that time t, well, you can see that the reaction rates are clearly different, because you notice that the slopes of the graphs are different. So the slope of the blue graph is less than the slope of the orange graph, which again is less than the slope of the red graph. So we can say that the blue reaction is going at a slower rate, the orange graph is at a faster rate, and the red graph is the reaction is going at the fastest rate. And so there may be a number of factors which influence this difference in the rate of reaction. So for example, as we move from blue to orange to red, the reaction rate is increasing because the temperature of the reactant is increasing, or possibly because the concentration of either A or B or both increases. Okay. Now I'm just going to make myself a little bit more space here, so bear with me a second. Okay, so that we're saying that by increasing the temperature, concentration, or the surface area of either reactants, this would result in an increase of reaction rate. And the fourth factor, as you probably remember, is if we introduce a catalyst to help the reaction go faster. Okay, so we may have a catalyst involved. Okay, so you may be asked to qualitatively analyze three curves like that. They may throw in another curve like this. The same reactants involved, still A plus B giving us C plus D, but this time the graph has a different shape. What this tells you is that there's a greater amount of reactants involved. So in this particular case, the mass of reactants involved in the reaction is greater.